All right, ready to go?
Yes, sir.
Good. Third presentation for this morning is by team 66.2. They will talk to you about their hydraulic bike design. Right away.
All right. Good morning, everyone. My name is Austin Roy, and along with Andres, Alicia, Jake, we make up team 666.2, and we're going to be talking to you all about our hydraulic bike design. Now, what we're going to be doing is designing and building a bicycle to compete in the Tour de Patrick. We're going to be utilizing hydraulics to transmit power from our rider to our wheels of our bicycle, and we're going to comply with our competition rules as necessary. We're going to be competing in a speed, coasting, and incline challenge. Some more details on that for the Tour de Patrick. The coasting challenge, we're going to be allowed to pedal for up to 100 feet, and then we're going to have to let the bike coast as long as possible. And we also have a speed challenge where we need to complete a course as fast as possible, and an incline challenge where we need to climb up an incline as fast as possible. Some rules that we need to consider is that we must design and manufacture the frame. We're limited to a maximum of 2 wheels for the bicycle this year, and we have to have some source of hydraulic transmission for our bicycle. Some of our customers include our primary customer, which would be our sponsor from Phillips 66. Our secondary customers include you all, the Capstone design panel, our rider, and the vendors that we use for our components. Some competing designs. Team 66.1 is a direct competitor for this competition. We also have to consider designs from the last year hydraulic bicycles, and we have a picture here of a Purdue's hydraulic bicycle, which they competed in a very similar challenge, and this is how they placed.
The functional requirements of our hydraulic bicycle are identical to those of a normal bicycle. However, the Tour de Patrick competition imposes constraints on how we accomplish function 1, connecting the components, and function 3, transmitting the pedaling power. We're not required to come up with a unique solution for the other 3 functions, so we are addressing them with traditional bike components. Our qualitative constraints are simply that the bike be ergonomic and maneuverable. We want our rider to feel balanced and to be able to completely control the bike while also not overexerting themselves. We have 6 quantitative constraints. We want the bike to accomplish a speed of at least 8 miles per hour. We want the hydraulic system to be at least 50% efficient. We want the bike overall to be at least 45% efficient. We'd like the hydraulic system to produce at least 0.2 horsepower. We want the frame and hydraulic components to weigh no more than 50 pounds, and we have $2,750 to manufacture and test our design. Our objective tree is based off of our functional requirements. Again, it's almost identical to that of a normal bike, except for how we address power transmission. For our design, we are interested in energy in the mechanical and the hydraulic domains. And our main concern is that the hydraulic system be able to generate enough fluid force to drive the rear wheel. So our bike is divided into 6 subsystems that address the functional requirements. Our frame connects all the components. The hydraulic drivetrain transmits the pedaling power. The crankset allows the rider to input pedaling power. The rear wheel system is driven by the pedaling. The steering system allows the rider to input steering control, and the braking system allows the rider to stop the bike. Now we will discuss our concept selection process for the frame. We considered 5 types of bike frames: a seated or recumbent bicycle, a conventional bike frame, a standing bike with hand and feet pedals, and a standing bike with feet pedals only, and finally an elongated frame. This is our decision matrix for the frame, and our datum was the conventional bike frame. As you can see, the elongated frame was the winner, and our main concern was that the bike provided enough mounting space for the hydraulic drivetrain. These are our first 3 frame concepts. Our first iteration is very similar to that of a normal bike frame, but we quickly realized our hydraulic components would be too big and we would need more mounting space. Our second iteration has these 2 bars you see at the bottom that allowed or provided mounting space for the hydraulic components. But when we studied the range of motion of the pedals, we realized that they interfered with the hydraulic system, which led us to our third and final iteration that you see. It provides sufficient clearance for the crankset, and the hydraulic parts are mounted onto the frame by removable plates.
All right, next is the hydraulic drivetrain. Our first design is the pump and motor. We'll start from the pedals. will pump fluid from our pump to our motor. And depending on that pressure and flow rate, we will spin the motor, which will spin our rear wheel since they are connected via sprocket and chain. The concern here is going to be selecting a pump that is efficient and works with our budget, and it can also fit with our frame. Our next design option is the same design, but now we include a accumulator. This will allow us to store energy via a high pressure fluid. From there, we will be able to get a higher torque output at the rear wheel. The concern here is that we are not allowed to pre-charge the gas bladder within the pressure vessel using an external power source. Design number 3 is the reciprocating gear valve, and it is based off of Pascal's law and inspired from the steam locomotive. So with this design, we will be able to maximize our efficiency using the ratio of the areas, and as well, we won't be using a pump or motor. So in the decision matrix, we see that the pump and motor design ranks the highest. This is primarily due to the criteria and weight, specifically the manufacturing complexity and also the cost. So our pump will be selected based off of our rider's input power, which is around 0.456 horsepower. So we need to make sure that our pump can provide a high pressure and a high flow rate using that power. And we need to make sure that it is cost effective and also the efficiency of the pump is high enough. So based off of this graph right here, we see that if we desire a high flow rate and a high pressure, we would need to increase the horsepower required to drive the pump. So we know that our input is around 0.456 horsepower. If we have a flow rate of around 0.5, which is the blue line, we will get up to a max pressure of around 1,500 pounds per square inch. Next, we will be analyzing the combinations of the pump and motor. So we are looking at the speed and time versus pump and motor size. Size is also known as displacement, and that's given as inch cubed per rev. So we're trying to find a pump and motor combo that gives us a speed greater than 6 miles an hour and under a time of 10 seconds to reach that max speed. The pump and motor combo that gives us this is a pump of a 0.24 displacement with a motor displacement of 0.18. So specifically, we will get a max speed of around 5.5 miles per hour at a time of 5 seconds.
Okay, so next I'll describe the hydraulic setup for us. Starting with the reservoir at the top of the diagram on the right, it will hold 0.22 gallons of AW32 hydraulic oil. Then coming out the bottom, following along the green line, will be a 3/4 inch flexible hose that leads to the pump's inlet. Then coming out of the top of the pump on the pressure side, it'll immediately branch off to a relief valve. And we'll set that relief valve to 3,000 PSI. And in the event of overpressurization, it'll discharge directly back to the reservoir. Now, going back to that T, we'll 90 out to a piece of 3/8 inch stainless steel tubing that leads to the inlet of the motor. And then out of the motor will be another 3/4 inch flexible hose leading directly back to the reservoir. And the picture on the bottom left-hand side is a cutaway view of that flexible hose that we'll be using. All right, so Austin's pedaling rate is around 80 RPM, and the pump and motor that we've selected, they operate more efficiently around the 500 RPM mark. So to address this, we're going to be using a gearing system of roller chains and sprockets, and the gear ratio from the pedals to the pump will be 60:9, and from the motor to the rear wheel, 9:50. The rear wheel's cassette will also have 9 speeds, ranging from 50 teeth down to 11 teeth. This ability to change gears will help the rider increase the bike speed without increasing his pedaling rate. So next we'll move on to concept selection for the remaining subsystems. That's the crankset, rear wheel, steering, and braking systems. And we'll accomplish this using normal bike parts. We'll either purchase them online or from local bike stores. And all of these are manufactured within the Code of Federal Regulations, Title 16, which specifies a life cycle of 5 to 10 years, which will be long enough for our system. And in some cases, it'll be more appropriate to buy gently used bike parts from Front Yard Bikes here in Baton Rouge. And we'll have those components inspected by Will Adams, the bike mechanic and welder there, to ensure that we're getting the best quality parts. And this would help reduce reduce wasteful spending on single-use parts. And these are some final renderings of our full solid model.
So before we discuss the analysis of the frame, I'm going to discuss the forces that resist the bike's motion. First of all, we have mechanical resistance due to friction between the components of the bike that are in contact, but these resistances are almost negligible and will be ignored. Gravitational resistance is constant if you are riding on flat ground, but when you go up a hill, the effect of gravity becomes much more severe. Rolling resistance is the energy lost due to the tires deforming as they rotate on pavement. And aerodynamic drag is the largest force resisting forward motion at higher speeds. It's a function of the surface area of the rider and the bike, as well as the bike's speed. And about 80% of the aerodynamic drag acts on the rider's body. So we're going to be addressing this with our rider's position. So all of these forces are overcome by the rider applying a pedaling force. The safety factor of a bike frame or a bike in general is not a constant value, and it actually depends on the load conditions. And the actual service loads a bike will endure depends on what the bike is designed for. So for our purposes, we define 3 loading conditions that are relevant to this competition. The main difference between these 3 conditions is their resistive forces, the pedal force required for them, and consequently their safety factor. Our starting from rest case has a safety factor of 10. Our coasting case has a safety factor of 9, and our hill climbing has the lowest safety factor of 0.8. The hill climbing load condition proved to be our worst case scenario that would most likely cause failure in the frame. So we applied these worst case scenario loads to a 3D SolidWorks model and used finite element analysis to compare our 2D safety factor approximation to the 3D approximation for the safety factor from SolidWorks.
Since we're building a frame in 3 dimensions, we considered using SolidWorks finite element analysis for the stress in the frame in 3 dimensions. If you look at the boundary conditions we set for our frame in SolidWorks, we set points A, B, and C, front and rear of the bicycle, to fix it from moving and allowing these points to rotate. And we have loading conditions at the handlebar and the pedals of the bicycle, as well as including the force of gravity on the frame. The element type we went for our analysis was a beam analysis to simplify the calculations. And when we use this, we found out that the maximum stress and displacement shown is independent of our mesh size. The reason for this would be that the maximum values are calculated at the joints of our beams using this element type, where a node is always going to be present. Our convergence shows that as we refine our mesh, degrees of freedom increase, our maximum stress and displacement are going to remain the same. Now, the main reason we wanted to use this FEA is to iteratively solve for our varying diameters and thicknesses of our tubes. We want to make sure this frame is as light as possible, however, being able to hold weight in our maximum loading condition. So we use this process to target at a factor of safety of 2 given our extreme loading condition. And we came up with a factor of safety of 2.14 considering the 3-dimensional model. The reason this is different from the 2D approximation is because now we're showing that we actually have two tubes near the rear of the bicycle.
The goal of frame design is to design a frame that is stiff in one direction while being flexible in another. The photo on the left shows the actual deflection that occurs in the axial and the lateral planes of the frame. And on the right, we have 2 photos that magnify their deflection. I want to point out that these are not to scale, but they show the general trend that the frame is axially rigid and laterally flexible. And this is what we were hoping for from our frame, because a frame that is laterally flexible in a bike is more ergonomic, intuitive, and rider friendly. And that was our qualitative goal for this project.
All right, so we are expecting a minor pressure loss of around 138 PSI. This is mainly due to the resistance of our fittings and our bends within the discharge of our pump and ends between the inlet of our motor. We've also created a model of our hydraulic transmission. This gives us a transient response based off of these system inputs. So the goal here is to compare these theoretical results with the results from our physical system that we will be fully assembling in the spring semester. All right, so in our model, we accounted for the pressure relief valve, the fixed displacement pump and motor, and also the efficiency of the pump and motor. All right, so in the first case, we are trying to apply load to the motor, which is the load to overcome rolling resistance, and that load is 0.135 pound-foot. And we gave the system a rise time of 5.5 seconds to reach 500 RPMs. This is the operational speed of our pump. So we're inputting mechanical power, which is our pump shaft speed and our torque. And from there, we'll convert it back out to hydraulic power, and we'll get our flow rate and our pressure. Our motor will accept that fluid power and convert it back out to mechanical power. But hydraulic horsepower, since being that it's a function of flow rate and pressure, we get our flow rate to be around 0.5 gallons per minute, and our pressure to be around 350 psi. Our resulting motor speed is dependent on the load, and we got around 600 RPMs of our motor after the rise time of 5.5 seconds. In case 2, we're trying to find the maximum load out of the motor with a rider input horsepower of 0.456. So with this input power, we're able to achieve a max pressure of around 1250 psi. This gives us a flow rate and a pressure that's very similar to the last case, but now our pressure is a lot higher because our load is also a lot higher. So now our motor is able to overcome a load of 1.54 pound-foot. And so we can see our motor will actually stall for the first 2 seconds. This is because the flow rate that is being provided to the motor won't actually start doing positive work until about 2 seconds. And from there, we will start to accelerate up to around 400 rotations per minute. So we can conclude that if the motor load increases, our rider input torque must increase, which will decrease our output speed. This is because horsepower is a function of torque and RPM also. And vice versa, if our load decreases, our speed will increase, but our torque that's needed to overcome that load decreases. Some considerations include that the rider input horsepower is constant. The rise time is around 5.5 seconds, which is based off of tests that we have performed, and as well that the load will vary throughout the operation and also depending on the competition.
So our biggest consideration for safety of the bicycle is our ability to brake within a reasonable time. So we have to look at our braking capability of our bicycle. Now, the braking system is similar to what you see on a normal bicycle. In this case, you have 2 levers, one at the handlebar and one at the wheel of the bicycle. The way we went ahead and figured out how we would be able to brake was to use a dynamometer to test our hand grip strength. We came out to a lowest value of 80 pounds, which we ended up using. And by taking the sum of the moments around the pins of these levers, we're able to calculate the output forces at these areas. Now, in the case of the handlebar, we're able to get a tension cable of 183 pounds. And when we translate that through to the brake at the wheel of the bicycle, the same tension is applied here. And then that braking force comes out to 1,320 pounds. That's the force of the brakes against the rim. Now, the actual braking force that is applied to the wheel in the direction you're rotating is only going to be 660 pounds because this is multiplied by the coefficient of friction of your brake pads as supplied by the manufacturer of 0.5. And then the force of friction between your wheel and the ground actually only comes out to 160 pounds. That means that we only need a braking force of 173.3 pounds to actually lock up the wheel and basically skid the bicycle. However, we wouldn't want to do that. We would want to apply up until this force and no greater. Therefore, grip strength is only needed at 21 pounds. This means we're well within our operating range. Now, if we assume that we can lock up the wheel of the bicycle, then we can use the work energy theorem to calculate what our minimum braking distance might be. This is a function of our force of friction, our braking distance, and the change in kinetic energy of the bicycle, assuming we're going to stop. The mass actually cancels out in this situation, making our braking distance a function of the speed of the bicycle and the coefficient of friction between the wheel and the ground, we come up with 9.4 feet at 15 miles per hour, which is within a goal set by the CPSC bike regulations. For our material selection, we looked at some materials that were popular in industry for bicycles, including carbon fiber, titanium, steel, and aluminum. Our main property considerations were to maximize our strength and stiffness and to minimize our density and cost of our material. The way we went about this, we use the Ashby charts to plot our material properties. The Ashby chart shows the properties of different materials. In this case, we're showing the strength versus density. And in order to use this plot, we have to define a performance material index. And this is based off of our specific application. This material index, we take the log of this material index to come up with a slope of a line to apply to this graph. And this line is going to pass through different materials. The point at which it passes through aluminum, titanium, and steel is going to be the same slope. Therefore, we can say that these are going to have the same, in our case, strength to weight ratio. And then if we move further up and to the left, carbon fiber falls above those. So we would say that carbon fiber has a better strength to weight ratio. And this is shown by the ranking in our charts. Aluminum, titanium, and steel rank the same. Carbon fiber ranks above those. The same method was used for the stiffness and density calculation, as well as the strength to cost per unit volume. This is how we got our ranking here for our materials. Carbon fiber actually ranks the best out of these materials. However, we have some additional considerations that we cannot calculate and such. The practicality of manufacturing carbon fiber would not be appropriate for the spring semester. So we considered steel and aluminum, which rank similarly. And the selection between those came down to what we're told about the weldability of these materials. And they said that steel would be the best option. Recommendations from different bicycle companies for the alloys of steel came down to these 5 selections. And we went with chromoly steel due to its high elasticity, strength, and density, and because it's readily available.
All right, so for the manufacturing plan, I'll begin with the frame. We'll send our SolidWorks model of the frame to VR3 Engineering, and they'll they'll notch all of our tubes for us in CNC machines. We also will hire a professional welder from Front Yard Bikes to weld our frame together. So combining these near perfect miters on the tubes, a specialty jig, and a professional welder, that'll really help reduce any manufacturing or errors due to manufacturing. After the frame is completed, we'll test the welds and loading on it, connect remaining subsystems, and then begin to mount the hydraulic system. So for the hydraulic system, first we'll build mounting plates for the pump and motor. And once these main components are mounted, we'll then that'll allow us to configure our chain and sprockets, mount the reservoir, fittings and hosing, and then we can begin setting, then we can set the relief valve pressure. All right, so testing for the frame, like I said, we want to use liquid penetrant testing to test the quality of the welds, and also strain gauges to test the deflection in the frame. And we can compare this experimental deflection against the theoretical deflections we came up with in the FEA. So testing for the hydraulic drivetrain, first we'll set the, like I said, we'll set the relief valve pressure using a pressure gauge. Then we'll monitor the system pressure while testing the bicycle on a stationary stand. After that, we'll begin practicing on the specific race courses that we'll be on. And then we'll also be able to test maximum speed, braking distance, turn radius, and maximum lean angle, which are common bicycle performance tests. All right, so safety considerations for our design. We'll have our rider wearing PPE. We're in accordance with CFR Title 16 bicycle safety guidelines, like Austin mentioned earlier. And we'll have the pressure relief valve in our hydraulic loop. Safety in manufacturing. Anytime we're around welding, we'll be wearing PPE, practicing proper tool handling. We'll also have our hydraulic components assembled by professionals. And safety in the environmental case, we'll properly dispose of all hydraulic oil, clean up any hydraulic oil spills that may happen, and recycle any bike parts. So for our budget, the frame and the hydraulic drivetrain, they take up the most of the budget with 29% and 22% respectively. But after you factor everything else in, we'll still have 18% of our budget left for contingency. Also, Parker will donate the hydraulic pump and motor which will then free up another $400 in our budget. So project milestones, we've already ran through what we've done this semester, starting with engineering specs, concept gen, component and concept selection, engineering analysis. And then in the month of December, we'll begin procurement. And then continuing in January, we'll also be performing component procurement. And then in February, we begin building the bicycle frame and connecting the hydraulics. By March, we want to have a fully assembled bicycle ready to test, and in mid-April, compete in the Tour de Patrick. Now, our COVID-19 contingency plan, all of our bicycle parts will be able to be assembled at one of our houses. The welding and the hydraulic assemblies are already being outsourced outside of LSU's campus, and we're well versed in digital communication where we could operate efficiently outside of campus. Special thanks to Phillips 66 for sponsoring this project. Also, our hydraulic vendor, our manufacturer, Parker, vendor Hydrodyne, and Front Yard Bikes. All right, Dr. Nick.
Thank you very much, Team 66.2. Let's see. We have Chris as the first customer to ask questions. Chris, would you mind asking the questions one by one
Sure.
rather than giving them all at once?
Absolutely. Okay. The first one of your objectives is efficiency goal, and I think it was 20% or so. But nowhere in your presentation did you talk about how you will evaluate efficiency or how you will measure it. Can you discuss that?
Yes, sir. So the manufacturer gives us performance curves for all of their pumps and motors, and we use those performance curves to calculate the various efficiencies of the pumps and motors.
Okay. I would have preferred if you've had something there. It's kind of nebulous to state a goal and not say how you're going to achieve it. But you kind of segued into the second question, which was, I don't think you discussed much about the motor and a pump selection. Can you address that maybe? Show me the slide.
Yeah, so the slide in the PowerPoint has like our goals for top speed and for the time it takes to reach that. So as our acceleration decreases as our top speed increases, basically. So we were trying to find a kind of the best in between fit.
Okay, I got that. I would have liked to see, for instance, one of the major engineering targets is in industry is to take a catalog of pumps and motors and to select one there. If you would have maybe showed the ratings or the page out of Parker's book where you picked all of that, it would have been a very...
Yeah, so this is their catalog right here. So that's where we get all of the different displacement sizes that we had to choose from.
Okay, my apologies. I somehow missed that slide.
Oh, no, sir. This was in the appendix.
Okay. All right. So that's excellent. One last question. Was there any allowances or considerations of utilizing an accumulator for storing pressure?
Right. So the thing about it, we wanted to use an accumulator because if we would be able to store energy, that's an awesome thing. It would help us out on the coasting challenge a lot. The only issue is accumulators are pretty heavy, and since we're not able to use an external power source to compress the nitrogen that would be in the bladder of the accumulator, we really wouldn't get as much performance that would really make it effective for our design. That's one of the constraints of the competition, is that no external power sources can be used. All power must be generated by the rider.
Okay, and finally, if was one of the other constraints that the bike only has 2 wheels?
Correct. Yeah. So like last year's designs, they all had 3 wheels.
Okay. In your slide 13, when you were evaluating which design to use, I think you showed a 3-wheel design, and if that's outside of consideration.
Correct. So that was a picture that we found on the internet. In our specific design, it would have been 2 wheels. We understand that.
Okay, that does it for me. Thank you.
All right. Thanks, Chris.
Thank you, Chris. I think next one up is Bob Jelly. Bob?
Okay, yeah, I'm here. Sorry. Really enjoyed the presentation. Good job, guys. Just to clear something up, in this picture here, the font, what is that? I can see it's got front and rear brakes, but on the detailed photos and slides where you discuss the brakes, you don't mention that, or you don't really show it. But just it is going to have front and rear brakes, right?
Yes, we do plan to have front and rear brakes. The reason for this, we actually only would need one front brake to brake the bicycle within that distance. However, we would like to have a rear brake in the case of, let's say one of the brakes fails. And of course, now, if you're braking, the rear brake would not be able to apply as much force as the front brake because due to the dynamics of when you're braking, your weight becomes shifted forward. That's why you're going to have more weight on the ground at the front, allowing you to essentially brake the bicycle in a shorter amount of time, distance.
Okay. Could you go to slide 23?
Sure.
So what this shows, if I'm looking at it correctly, is that the outlet from the relief valve back to the reservoir and the outlet from the motor back to the reservoir are co-mingled. And that may be okay in this case, it probably is, but in general design practice, you try to avoid having any relief valve's outlet flow have to compete with another source of flow. So, but if you're going to do that, if you're going to commingle them, you have to calculate what that back pressure on the release valve is going to be by forcing it to mix in with another stream. So, my suggestion would be to give the relief valve outlet its own entranceway into the reservoir, not have it commingle with the motor outlet.
That's a great point, and it really wouldn't be too difficult for us to do. So that's definitely something that we'll consider heavily.
Yeah, it's just in practice in industry, you would need to account for those 2 streams trying to mix with each other. So, yeah, so yeah, if you can do that, if you can give it its own entranceway into the reservoir, I think that would be preferable.
Will do.
Other than that, I did have one other. I'm sorry. Slide 48. You say that you're going to do liquid penetrant testing of the welds. I'm not telling you what else to do, but I'm just saying that these welds are critical to the safety of the rider. And so I don't know whether it would be appropriate to do a test coupon and destructively test it just to prove the weld quality and strength, or whether there's another non-destructive test you can do on some or all of the welds to ensure that you have good fusion. Because I've heard of cases on cheaply made bicycles, not homemade bicycles, actually, professionally made bicycles that failed, had welds failed, and it could really injure the rider. So just give it some thought on whether the liquid penetrative testing is good enough to prove the quality of the welds.
Thank you for that suggestion. You're right. This is just a visual inspection, and it doesn't tell you the full story of the weld. And we'll definitely look into that.
That's it. Thank you.
Thank you.
All right. Thank you, Bob. Next one up is Richard Goda.
Yeah, you can go back to slide 23 because that's really where most of my questions arise from part of it. Okay, you have in here, you have your reservoir and your hydraulic hoses and your tubing, and you got, 3/8, half-inch, and 3/4 tubing. You never really said how you sized any of that stuff. And you came up another place with a pressure drop, which is all dependent on flow rate, tubing sizes, and this kind of stuff. Where are the numbers that go with that, and why did you select some of this stuff?
All right, so the size of the tubing, that's all going to be dependent on the inlet and the outlets of our particular pump and motors. That's how we based the sizing of our tubing. You don't want something too small or too big. You want to match it up just right. And then once we got those sizes, that's how we did the minor pressure loss calculations.
So the tubing size is not dependent on the ports in your pump and motor. The tubing size is dependent on your flow rates and expected pressure drops. So just because the port's 3/4 doesn't mean you have to use a 3/4 hose. I don't think you're going to be running this equipment anywhere near its max capability, are you?
Oh, excuse me. We don't expect to. No, sir.
Well,
but the relief valve is there just in case.
Well, the relief valve's a pressure thing.
Right.
But you're talking about needing to minimize weight and other things. Why is, the tubing can be a whole lot smaller. You're looking at low flow rates compared to what the pump could produce if it was turning, 3,500 RPM. You're not going to turn it that fast, are you? So you could make the tubing smaller, which would cut down on some of your weight issues, and your pressure loss penalty may not be that great due to the fact that you have very low flow rates.
Gotcha. That's a good point, and all I could say at the moment is that we'll evaluate it further.
Now, the other one is that you didn't mention, what are you doing with how are you rejecting the heat that all this stuff is making?
So
or did you even think about that?
We did, and the manufacturer of these pumps and motors, they basically said, like you said, we're not going to be operating at the maximum operating points of these motors normally, and so that's where we kind of said, okay, well, we don't really need to consider, or it'll be a negligible thing, heat in the system.
Well, it's not negligible if you got somebody that could touch it. How hot is it going to get?
That is something that we should, I guess, look into more. However, in terms of touching it during the race, Austin will be far enough away from actually touching him physically, but it is a safety consideration that we really haven't dove into.
Well, I mean, just because while he's, once you get off of it, if it got hot, it's going to stay hot.
Correct. Good point.
And so, again, why did you put them, you made the bike longer because of the configuration you have for where you're putting the hydraulic drive.
Yes, sir.
The beauty of hydraulic drives is that the hoses are easy to route wherever you want them.
Right.
So did you look at putting the drive points at different places on the bicycle?
Slide 24. Yeah, we did. So, but if you look here to use that rear derailleur, it's on the cassette to change gears. The best position for the motor is going to be is where you see it now, right underneath the frame.
Well, in line with your typical one.
Correct.
Okay.
And there's really, our frame would already have to be elongated to accommodate the position of the motor. So it just made sense to stack the pump right on top of it.
Well, why would the frame have to be elongated because of the motor? Because
you see where the
pedals didn't hit wherever you stuck the pump, which could be a lot higher up, even right right at the top part of the assembly.
It could,
by the fork, where the fork attaches. And that chain could go up vertical as opposed to being in the bottom part.
It could. However, the current configuration also provides a lower center of gravity, which will help in maneuvering. And if the pump and motor are farther away, it would increase the amount of tubing and amount of fluid needed in the system. That would increase weight for us. We do believe that this is the optimum placement of both the pump and motor.
That's not a good statement, because the amount of weight you're going to increase based on the fluid and tubing sizes is going to be very minimal. I mean, you're talking, you're not talking high pressure or large diameter hoses. But like I say, I mean, because changing the length of the bike also affects maneuverability. And the last thing is, you talked about loads. You never talked about impact loads after you made the frame bigger. And our wonderful Louisiana streets are bumpy.
Yes, sir. So when we considered our 3 load conditions, we did neglect to consider impact loading. Our hill climbing situation was our best simulation of the worst case scenario for the stresses that would be acting on the bike. In terms of impact and the way we intend to use this bike, a normal bike you would ride really fast, go around corners, and maybe get a little risky with it. Whereas in this case, we're going to keep things very, very tame and simply try to accomplish our speed and our efficiency goals. So we're not intending to impose any extremely large impact forces, but we did neglect to account for potholes or anything like anything along the road that might force larger impact loads through the frame. We generally didn't consider a suspension system for the front fork or for the frame in general, because this wasn't mountain climbing type conditions.
Well, I don't talk, I'm not worried about a suspension system, but the fact that you made the bike longer and you didn't account for the fact, well, what happens if we drop it? When you're unloading off the truck and it falls 3 feet and hits the ground.
Mm-hmm.
Again, the bumps in the road that people are going to, obviously your intent is not to go mountain climbing and jumping off ramps,
Mm-hmm.
but you still have to consider that for the safety side, because you could hit a curb and hit a bump or whatever. And then again, just like the welds, if the bike comes apart, you've now hurt somebody, likely.
Yes, sir. We did not account for like unexpected impacts like that, or any, we all our considerations stayed with what we expect to do with the bike. I think we failed to look at the perspective of, okay, what if we do something we didn't mean to do? I think that's a very good point, and we're definitely going to look into that and look into its ability to withstand.
That's it.
All right. Thank you, Richard. I have a general question. Just, looking at this from a large distance, if you will. What is the point of having a hydraulic system if you're not going to use that as an opportunity to provide some energy storage? Right now, the current design simply introduces a hydraulic motor pump reservoir combination that simply transmits power from one chain drive to another chain drive, and therefore basically it reduces the efficiency by introducing an additional process in the transfer of power. At least my perception was that use of hydraulics should take advantage of the opportunity to actually store some energy. So I'd like a little bit of elaboration why you actually did. I know you showed decision matrices and stuff like that, but decision matrices can be rigged. And I'm not saying that you rigged them, but what I'm saying, can you give me a rationale why you didn't take advantage of the energy storage
Yes, sir.
that your hydraulic motor pump and accumulator would afford you?
Right. It comes down to the weight of the added weight of the accumulator. We couldn't justify adding that much weight to the system. I mean, those could get up to anywhere from 30 to 50 pounds for the sizes that we were looking at. And to get the maximum performance or an acceptable performance out of an accumulator, you have to pre-charge it with nitrogen gas to about half of the system or half of the operating pressure of your system. So since we're not able to use an external power source to compress the nitrogen gas in the bladder, we wouldn't be able to achieve that half system pressure target value, meaning that there would be we would only be able to build up a little bit of extra pressure in the accumulator, and there would end up being a lot of leftover fluid in the accumulator that goes unused. We would want the accumulator to fully empty while we're using it, but because of the design constraints, we would only be able to empty it partially. So that's the rationale behind not having an energy storage device in the system.
Got it. So the key thing here is that the interpretation of the rule
Right.
of no external power does not apply strictly to the period during which the bike is operated, but how it's also prepped, because you can do the compression, you can pressurize before you enter into operating mode, right? And that's your
Right.
initial condition. So it is clear that no external power means
right. It would have to be power generated by the rider.
By the rider at any time.
Correct. Yes, sir.
So basically, the only thing you could get away with is having the rider pre-pedal and build up pressure, right?
Correct. And then the issue with that, though, is you're pumping in that fluid to the accumulator, but it isn't pressurized. It isn't pressurized with nitrogen gas to give you the maximum output. Okay, gotcha.
All right. Thank you very much. And we'll resume at 11.